Kia ora, year 12 and 13. In this video I'm just going to do the identity work from practice task B, which is quite a tricky proof question. And so we're trying to prove that this is equal to this, right? So this comes after we've had a look at the graphs of the two sides, and we've talked about the graphical features here. And then we've looked at this and we've said that it's sinusoidal, and we've got, again, an excerpt, and we've got points, and I'm making that up. I actually haven't done that for a while on this practice task, but this is the bit where we go and we match up the features. We say, look, the amplitude's the same, the period's the same, the vertical shift is the same, there isn't one, blah, blah, blah. And we've said, okay, so the graph features are the same, so the two functions, so this statement is always true. And now we're going to go on and we're going to prove that using identities. So I'm going to start on the left-hand side, but you can see that the right-hand side is kind of worse than usual. So if you just start straight into it, chances that you get all the way through, I think, are quite low. It's well worth just expanding the right-hand side like this to see what we've got coming up. So we've got 4 cos x sine squared x minus sine x. And then what's next? So we've got plus 4 cos squared x sine x minus cos x. And that's as far as I think you need to go. But the good thing about doing that is that if you've got that sitting there, you can see roughly where you're trying to get to. The other thing to notice in here is that here we've got a 3x over here, and we've got x, x, and x here, but we've got a mixture of cosine and sine. So straight away you should be noticing a few things. You should be thinking that that 3x is probably eventually going to need to be broken out into a 2x plus x, and we know that we'll have some exact values going on with sine and cosine of pi on 4. So just brushing up on our special triangles, we know that sine of pi on 4 is the same as cosine of pi on 4, and that's going to be 1 on root 2. Okay, so let's just get into it, and we're going to start on the left-hand side and work our way through. So we'll start by just doing the obvious steps. So you need to be really good with your compound angles. We've got 2 sine 3x cos of pi on 4 minus 2, right, don't forget the 2, minus 2 cos of 3x sine of pi on 4. So quickly that gives us 2 times 1 over root 2 sine 3x minus 2 times 1 over root 2 cos of 3x, which equals root 2 into sine of 3x minus cos of 3x. So you should be feeling pretty good at this point, because you can see we've already managed to get the root 2 there. What we've got to do now is somehow show that this is equal to all of this. So let's break down the 3x. I'm going to do it over here because I think OneNote is going to glitch somewhere on the right hand side of my screen. So we've got root 2 times sine of 2x plus x minus cosine of 2x plus x. And again, we're going to do the obvious things. So apply our compound angle formula, and we get sine 2x cos x plus cos 2x sine x minus cos 2x cos x minus sine 2x sine x. And I'm going really slowly with this for two reasons. I want the person reading it to see each step making sense, but I also need to be really careful here where I've got a minus, that minus and a minus there. Just watch out for that. Now in the next line, just having a look before I do it, sine of 2x has only got one option for what to do next, and that comes in twice. But I've got cos of 2x coming in, and there are 3 options there. And there's no reason that I should use the same one for both. So this is why I think it's a good thing to have done this expansion here, because I think this is where the proof starts to get a little bit, just a tiny bit more creative than usual, which makes it a really cool proof. I really like this question. You may not feel the same way right now. Here we go. So we've got 2 sine x cos x cos x plus, let's just leave that sitting there for now, and we'll leave this sitting here for now, so minus cos of 2x cos x, and then I've got plus 2 sine x cos x, sine x. So I can't clean up too much, but I can write this as 2 sine x cos squared x plus 2 cos x. Sorry, this one here. Yep, cos x sine squared x. So that's those done. Now let's have a look at where I'm trying to get to. I want to end up with 4 cos sine squared x minus a sine x and minus a cos x. And also notice that I don't have any constant terms coming in here, right? And so when I do my cos of 2x's, I want them to be such that the plus 1 and the minus 1 are going to undo each other or reverse each other. So we're going to try this, and if it doesn't work, we can try it again. If we do this, we've got a plus 1 coming in here, and then we've got a minus negative 1 in here. That's not going to work. So instead, I'm going to try this. 2 cos squared x minus 1 sine x plus 1, whoops, sorry, that's a minus. Oh, see, it's so easy to get your signs wrong. Right? So there's minus 1 minus 2 sine squared x cos x. Now, I think that's going to work out fine, right? Because we want to have, in my final thing, we want to have a minus sine x here and a minus cos x here. And that's going to work, right? Because when I expand that, I'm going to get this. In real life, what you're probably going to do is you might do this wrong, right? But doing it wrong, you'll notice that something's going wrong with this, and then you can play with the other one. So I'm going to come back and actually do this going the wrong way at the end of this correct version. And we'll just see how you can get yourself back on track. So in here we've got 2 sine x cos squared x plus 2 cos x sine squared x plus 2 cos squared x sine x. So that's looking really good because that's going to match up to give me 4 of those. Minus sine x minus cos x plus 2 sine squared x cos x. Let's clean up the like terms. So we've got 4 sine x cos squared x plus 4 cos x sine squared x. Here and here, minus sine x minus cos x. Now we should be feeling really good, right, because we've already expanded up here, so we've done that. But to do it properly, what I'm going to do now is I'm going to do two-stage factorizing on this so that we get all the way through to the start. So let's just put a box around this and then a box around this. So this equals root 2 into 4 sine x cos x. And here, looking at my common factor, times cos x plus sine x minus sine x plus cos x for that second one, which is root 2 into 4 sine x cos x minus 1 times cos x plus sine x. And we don't need that square bracket there. And that is equal to the right hand side as required. Now don't turn off the video because I'm going to go back now and I'm going to show you what happens if you are sitting there and you've done the obvious things and then you pick the wrong thing to do, right? So the last thing I have to say is this. So the equation is always true. Okay, so we have to finish off with that statement because that's the question we were asked about. Okay, so let's get rid of all the stuff that went really well. I'm going to go back and now I'm going to use the wrong double angle cosine and I'm going to try and help you see how you can get yourself out of the big hole. But it really does come down to keeping an eye on where you're trying to get to, right? It's like kind of when you're learning how to drive a car. So let's delete this double angle magically with the pen. Let me get rid of that one. we're probably not going to use the cosine minus sine squared one, right? Because that's just usually a bad idea. But in here, now I can't remember what I used. So the correct one to use here was the 2 cos squared one. So let's do the other one. Let's do 1 minus 2 sine squared. And then let's do 2 cos squared x minus 1. The thing that you notice straight away in there, and the reason it's getting worse, is that you get the first term and the second term, and then you get a plus sine x, and you get a plus cos x from in here, right? And seeing that, if you've looked at this, even if you haven't expanded it, you should be seeing that you should be getting negatives of those, right? So that's your first clue that you've flipped them the wrong way around. The second clue is coming because instead of getting stuff that's going to match up to here, you're getting cubics terms coming in. So you're getting 1 minus 2 sine cubed x minus 2 cos cubed x. Right, so you can stop and have a look at that, but it's pretty clearly going bad, right? Because suddenly you've got 1, 2, 3, 4, 5, 6 terms. There's nothing cubic going on up here. So go back to the start and have a look. So hopefully at that point you're going, well, I didn't have to choose that one. I could choose something else. And you might instead choose to do, the first thing you might try and do is the other one here. And you might try and do that one again there, right? But eventually, I think you've done enough identities work that you should be able to spot that you're sort of getting there, but you're going to have the wrong sign on one of those, right? So often choosing the correct double angle for cosine can make the difference between a hard proof going really, really well, and you feel like, wow, I really smashed that out, or getting tied up in knots. Okay, I don't know if anyone's out there still listening or not. Hopefully some of this made sense. Daniel, I hope this helped a wee bit. This is definitely at the challenging end of level 3 trig proofs, but there's a lot of good revision in there on both compound angles and double angles. So thanks for watching all the way to the end.